Hello, everyone. How are you doing today? Weekend treat everybody all right? Seems okay. All right. So, our plan for today is to continue in chapter 6. We are progressing through our understanding of Laplace transforms and using them to solve differential equations. Okay. So, the main thing that we are going to be adding to our ability to solve differential equations has to do with discontinuous functions. All right. Um, for discontinuous functions, the basic idea is that integrating smooths these out. So when we apply something like the Laplace transform, which takes the integral of an object that expresses that object in a new context, and in that new context, those discontinuities are way less of a problem. Okay. And so what that allows us to do is change the types of things, especially the types of things that we place on the right-hand side of the equation as our forcing functions, okay, the non-homogeneous part of the differential equation, and to be able to deal with those effectively. The first of those types of examples that we're going to be working with is called the unit step function. The textbook uses the following notation for this function: u sub c. It is a piecewise defined function that is equal to 0 for values of t that are less than c, and 1 for values of t that are greater than or equal to c. Okay? So, graphically, very simple to understand what this looks like. You pick a value c. The c doesn't need to be a positive number. I'm just writing it because it's easier to draw the picture this way. The function is 0 up until that point, at which it jumps to 1 for its value. Okay, so it is a so-called unit step function because the size of the jump is 1. Now, if we need the jump to be bigger, we multiply by a number. Okay, so you just take alpha times uc of t, and then instead of the size of the jump being equal to 1, the size of the jump is equal to alpha. Okay? It's also possible for us to talk about a downward step, in which case we would want the function to start out at 1 and be 0 for values beyond. And the way that we do that is just to take 1 and then subtract from it the unit step function. So simple enough. Okay. Now, the idea is that we can combine these in order to be able to create whatever piecewise constant function we would like. So we can have step ups and step down, steps of different sizes, in order to get as complicated of a expression that we want, where the whole thing looks like this. Piecewise constant. Okay. Now, before we get into that, there's one other thing that I want to note. And for those of you who interact with computer algebra systems or other things, instead of calling this the unit step function, this is sometimes also referred to as the Heaviside function. All right. The Heaviside function is given the notation capital H of t, or sometimes theta of t. And it is piecewise defined to be 0 for values of t less than 0, and 1 for values of t that are greater than or equal to 0. And if you need to shift this, which is the role held by C in the notation that is used by the text, you would use the rules for shifting functions left and right that you are familiar with back from algebra classes. You just change the argument to t minus c, and that's a rightward shift of t. Okay. The computer algebra systems, for example, Wolfram Alpha or other things, don't use this version of the function. They use this one. So you need to know those things so that you can check your answers if necessary. Okay. So say we wanted to sketch the graph of this expression. Say that t is greater than or equal to 0. So we have u sub pi of t minus u sub 2 pi of t. Okay. We should know that pi and 2 pi are important. 1 is also probably important, maybe 2. Okay. So what does the graph of this look like? Okay, that's what the graph of the whole thing looks like, right? So if we have this set up, it's 0 up until this value, and then it steps up to 1, and then it's 1 up to this point, and then it steps down. And it's 0 for the rest of the values for t. So piecewise, what that looks like is 0, 1, and 0. We can break it up into 3 pieces. Function's not defined for values of t that are less than 0, so we stop there. So piecewise definition for the function looks like this, and we see that the figure looks like that otherwise. Okay, now we could, if we wanted to, think about those vertical lines as being drawn in, And if you were to look at an object like this, perhaps in an oscilloscope, you would see that the way that this would be drawn would be like so. Okay. Because of that, this particular figure is sometimes referred to as a rectangular pulse. All right. There are a lot of applications in which you would use this as a forcing function for the right-hand side of a differential equation. Okay, I mentioned the idea of an oscilloscope, right? If you've ever seen an oscilloscope in real life, okay, one of the buttons on the oscilloscope is create a periodic rectangular pulse. Okay, mathematically, we model such pulses using combinations of these step functions. Okay. The amplitude of the rectangular pulse is given by whatever number, should I choose to have a number, I multiply my function by, okay, and so on. Okay, so what I'm writing down here is a piecewise constant function. It's 3 between 0 and 3, -1 from 3 to 5, 5 from 5 to 9, and 2 beyond 9. And what we want to do is make sure that we understand what this looks like, and also to be able to write it in terms of Heaviside functions. So we want to be able to make this expression. All right. So if we start off at 3, what should be the first component of our function f of t written? We'll start off with unit step functions. This function's constant except when it changes, right? So what's a constant function whose value is 3? Okay. I'm not asking these questions to be a pain in the butt, all right? I'm asking these questions because one of the things that you will often have to do as part of these problems is convert a piecewise defined functions to be written in terms of Heaviside functions or unit step functions, because unit step functions are the ones that we are going to know the Laplace transform for. We won't know the Laplace transform for this. Okay. All right. So I need to now step down from 3 to -1. How do I do that? We subtract 4, but not until when? Until t equals 3. How do I represent something not happening until I get to t equals 3? Huh? In this case, since we're using the unit step functions, we don't turn on that jump down until 3. Okay. Next thing that we need to do is jump up to 5 at 5. So what do we write? Okay, so plus 6 u5 of t, because the distance between -1 and 5 is 6. I'm jumping up, so it's positive, and that doesn't happen until t equals 5. All right, what about the last one? We have minus 3 u9, right? Step down of 3 doesn't happen until 9. Okay. Now, the other thing that we will need to know is that this can equivalently be written in terms of the unit step function. Or sorry, the Heaviside function, pardon me. These two things should be the same. All right. So if we switch over to Desmos, we'll see if this does indeed work the way that it's supposed to. Okay. So we'll make u sub c of t and have that be equal to piecewise defined function. All right. We're going to make this equal to 0 for t less than c and equal to 1 for t greater than or equal to c. I have to remember how to do. Oh, okay, sorry. I have it backwards. That's the problem. All right, so it should be t less than 0. Sorry, t less than c, 0. And then t greater than or equal to c, 1. I'll add a slider for c. Okay, so the idea here is that now I can move what the value of c is, and it changes when this thing turns on. Make sense? Okay. Now, can I? Okay. What I'm instead going to do is I'm going to make this a function of two variables. Okay. So that I can plug in different values for c to change what that constant looks like. All right. So now what I should be able to do is do 3 minus 4 u sub c of, and now I want this to be f of t is equal to t, and we pick a value for t, which is 3, and then we subtract from that, or sorry, we add to that 6 u sub c t, and then this turns on at 5, and then minus 3 u sub c t, and this turns on at 9. Okay, we ask ourselves, does this satisfy the conditions it needs to satisfy? And then technically this isn't supposed to be turned on until t greater than or equal to 0. Okay, but our conditions were 3 and then -1 and then 5 and then 2, right? So it's 3 from 0 to 3, -1 from 3 to 5, 5 from 5 to 9, and then 2 beyond 9. Okay, so this has given us what we wanted, right? Now, alternatively, we could have defined the Heaviside function to be for t less than 0, it's equal to 0, and for t greater than or equal to 0, that we get 1. Turn this off, okay? And then also write 3 minus 4 times h of t minus 3 plus 6 times h of t minus 5 minus 3h of t minus 9. Okay, it covered up the graph because it's the same graph. All right, this one is the one that you would more likely type into some computer system. Okay, Desmos has the flexibility for us to be able to do a fancier version of what it is we're talking about, but okay. And then, sorry, I will also add the domain restriction to this in order to get rid of this part. Anyway, it all works. Okay. So when you are working with discontinuous functions, this is the language in which we write it. So now we will be taking the Laplace transform. We want to take the Laplace transform of the unit step function concentrated at c. It's the integral from 0 to infinity of e to the minus st u sub c of t dt. We know from the piecewise definition of this expression that it is a 0 before c and then 1 after c. This allows us to very easily break its integral up into two parts. And we've done integrals like this before, right? Except instead of plugging in 0, we're plugging in c. The other part goes to 0 because we have a negative exponent going off to infinity. All right. Okay. If we plug in c equals 0, we get e to the 0 over s. E to the 0 is 1. Okay. So the Laplace transform for the canonical Heaviside function, the one that's centered at 0, okay, is the same thing as the Laplace transform for 1 because of the necessity that s be a positive constant. Okay, So we get this simple expression here. Things seem fine. Okay. Now, one of the really powerful uses for this is related to the idea of choosing a shift value. Okay. If I have a function g of t that is piecewise defined and it is 0 for values of t less than c and equal to a shifted function for values of t greater than or equal to c, okay, it's going to turn out that this is equivalent to this expression here. Okay, so what this represents is a function getting turned on at a particular value. All right, so we get rid of some of our extra stuff over here and then take a look at this. Okay, what you can do is we can define an f of t that's equal to something like sine of t. Okay, and I can define a g of t that's equal to u sub c of t, and then I'm going to pick a as my shift. Actually, we'll choose h for the shift, horizontal shift. And then f of t minus h, we'll add a slider here, okay? And what you see is that as we change the value for h here, what it does is it horizontally translates the function, but the function does not turn on until we get to whatever the value for c is. Okay. Now, this again is a very important type of idea from the perspective of maybe doing modeling using circuits. Okay. You can program some kind of condition that has a time window, all right, or that doesn't activate until after the system has been in motion for several seconds or something, all right? And you don't have to do anything other than understand what this base function looks like in order to be able to set the condition to be whatever it is you want it to be. Okay, I can choose some other function here, and I get the same thing. And this time we have a jump discontinuity. And that slides with it. Same thing happens. We get the horizontal translation of the function. And this can be as complicated as we want to make it. Here we have a parabola. All works the same. All right. Make sense? Okay. So with this new tool of step functions in mind, we can now start thinking about discontinuous forcing functions. So let's look at the following example here. We're going to pick some easy initial conditions for this one. But our forcing function is going to be something that features a discontinuity. It's going to be 1 between 5 and 20, inclusive on the left, and it is going to otherwise be equal to 0. Okay. We know the Laplace transform for Heaviside functions and things like that, so we're going to need to convert this into the language of step functions. Since it's 0 before 5, okay, we don't have anything to add, right? And then it turns on and then steps up from 0 to 1 on this interval. And at the end of this interval, it steps down. Following along with what we talked about earlier, representation of that is u5t minus u20t. And what we're going to need to do now is, with this understanding, work on our differential equation. So we replace the expression on the right-hand side with this equivalent one. And now take the Laplace transform of both sides of the equation. Okay. Using the identity that we had from last class, we will convert these derivatives. I'm going to go ahead and expand this expression so that we can see everything it is we need to see. Okay, again, I'm just used to writing the curly braces. If you want to use these types of brackets, that's fine. It's up to you. Okay. First term, we're going to have 2 times s squared capital Y of s minus s y of 0 minus y prime of 0. We're going to add to that s y of s minus y of 0 and then we will add to that 2 times y of s And then on the right-hand side, this is going to be e to the minus 5s over s minus e to the minus 20s over s. All right, all make sense? By the initial conditions, all of those are 0. All right, what that leaves us with is 2s squared, capital Y of s, plus s, capital Y of s, plus 2 capital Y of s is equal to the right-hand side. And on the right-hand side, we may factor the capital Y of s. On the left, we can factor the 1 over s. And what we want to do now is to isolate capital Y of s by itself on one side of the equation. Make sense? Yes. So for determining what's going to happen when we apply the Laplace transform, for this expression here, for instance, we have this expression. Okay. Now, the parts that I have marked on screen right now, that is an identity and it always happens that way. Okay. You need to make sure that you have the initial conditions too, though. All right. So here we have an easy problem because those values are both 0. In general, they will not be. And when they're not 0, the answer is affected by it. Yes. And when they're not 0, the characteristic equation will always still show up. There might just be extra things that go here in addition to the expression for the characteristic equation. And if you have this extra stuff, it needs to get moved over to the other side before you divide by whatever this is. All right. So we have this expression here. All right. Our step always when we're dealing with Laplace transforms is I have to look at this and then figure out what on the Laplace transform table gives me a path forward. So either in your notes or your textbook or wherever, you need to open up the Laplace transform table. I'm going to use the version of it that we have on our notes page. And the thing that we have for our expression is stuff in the denominator and then e to a number times s in the numerator. So if we look at the table and we scroll down to near the bottom, the line that is going to be the one that's important to us is line 13. Okay. What I have is e to some number times s times some function. All right. Now, this function, f of s, if I look at the inverse Laplace transform side of it, we see that we have a Heaviside function and then also a shift of that original function back in the time domain. Okay. And so this is going to be the key that we need in order to go backwards. So looking at this expression here, we see that I actually have two versions of that formula. What I need to do is I need to rewrite this as e to the minus 5s over that denominator minus e to the negative 20s over that denominator again. Now, in the formula, it just said that it was some function, right? Some function that I know the inverse Laplace transform for. Okay, what I'm going to do is I'm going to encapsulate this function by just calling it capital F of s. All right. Now, it is the function 1 over s times the quantity 2s squared plus s plus 2. Okay, that means that this above line here can be rewritten as e to the minus 5s f of s minus e to the negative 20s f of s. All right. I'm going to solve this problem in two stages. The first, find the inverse Laplace transform of this expression. Then, after I know the inverse Laplace transform of this expression, I use line 13 twice in order to figure out the inverse Laplace transforms of these expressions. Okay. You will often have problems where you'll get something that looks like this, and the way that you handle it is to give the rest a name, find its inverse Laplace transform independently, and then just write down the answer in terms of shifted functions. So that is what we'll do. Okay. So what we're looking for now is what is the inverse Laplace transform of capital F? It is something that we're going to have to use partial fraction decomposition on. Okay. Looking at this expression, is that quadratic reducible? Does it factor? Do we know? It doesn't look like it, right? So, because it doesn't factor, we're going to have to deal with it. And using our, hopefully, memory of partial fraction decompositions, we know that this is the setup that we need in order to solve our problem. Okay. So the idea is that we do the necessary multiplication to give these things all a common denominator, and then set the numerator of that expression equal to our original expression, and determine the values of the coefficients a, b, and c. So we have a times 2s squared plus s plus 2 plus s times the quantity bs plus c. Expanding everything out, we're going to get 2a squared. Sorry. I'm going to be clever and try to do this all at once. Dangerously. All right. So the first thing that I'm looking for is the stuff that's going to have s squareds in it, which is going to be a 2a and a b. The second thing that I'm going to look for is the stuff that's going to have s's in it, which is going to be an a and a c. And then the third thing is going to be the stuff that's constants, which is just 2a. All right. Now, if the algebra for doing that way is going to cause you to make mistakes, don't do it this way. Just multiply it out, or multiply it all out, and then group. Okay. What this does is, because polynomials are equal if and only if their coefficients match, then it gives me a system of 3 equations and 3 unknowns. 2a plus b has to be 0, a plus c has to be 0, and 2a has to be equal to 1. That means that a is equal to 1/2, c is equal to negative 1/2 because c has to be the additive inverse of a, and b has to be equal to negative 1 because this equation has to be 0. Okay, we have our coefficients. All right, that is to say that capital F of s is equal to 1/2 over s plus negative 1s minus 1/2 divided by 2s squared plus s plus 2. This can be rewritten as 1/2 times 1 over s minus s plus 1/2 over 2s squared plus s plus 2. Okay? This one's done. I know what the inverse Laplace transform for 1 over s is. It's 1. Okay? This I have to do some work on. Okay? So if we isolate this expression, I can factor a 2 out of the denominator. So that I have 2 times the quantity s squared plus s over 2 plus 1. All right. I'm going to need to complete the square in that denominator. Okay. Also, for simplicity, I can think about this 2 that I factored out as just 1/2 times the rest of this. Right. So that denominator is now separate. Okay. When we are thinking about completing the square, This is the expression that we have, right? Okay. S is equal to A in what I have over here. Okay. 1/2 is 2 times B, which means that 1/4 has to be equal to B. Does that make sense? All right. So that's how I figured out what B was. Okay. Now I want to complete this square. In order to do that, that means that I have to add and subtract B squared. So 1/16 minus 1/16, and then I have 1 left over from the expression that was already there. Make sense? Okay. So now we have in our denominator s squared plus s over 2 plus 1/16 plus 15/16. This is a perfect square. Okay. Now, I'm a little bit more used to looking at Laplace transform tables than everybody else. But the thing that we've been working towards here is lines 9 and 10, where we have a square expression and then added to that a number that's squared. Okay, so that's why I wrote 16 over or 15/16 as the square root of 15/4 quantity squared to conform to that expression. Make sense? Okay. So the next part of what we have to do is continue to match the form for 9 and 10. 9 and 10 have specific requirements for what the numerator has to look like in order for the Laplace transform inverse expression to work. All right, so we have to make sure that the constant's the right thing, and then once we have the right constant, then we can use the formula. Okay, so we're getting close, a little bit more work to do. So we have this, and we want to start putting everything together here. One of those expressions requires that our thing in the numerator match the thing that's in the denominator here. Okay, so I need this to be 1/4, so I need to split off 1/4 from 1/2. So instead of writing it as 1/2, I'm going to write it as 1/4 plus 1/4. And then the rest of this like so. Okay. I'm allowed to split fractions by separating sums or differences in the numerator. So we're going to do that. And when we make this separation, This part is done. Okay? But I need to deal with this. Make sense? Okay. Now, in order to finish the second part, this value has to match the inside of that square. I multiply by 1. After multiplying by 1, I can change how the expression is written. To make it look like that. Okay. This part here has an inverse Laplace transform. It looks like this. This part here has an inverse Laplace transform. It looks like this. Okay. Those are both known inverse Laplace transforms, except we have constants being multiplied times them for what's going on. So now, f of s is equal to this. Okay. Lowercase f of t is equal to 1/2 e to the minus t over 4 times cosine of radical 15 over 4t plus 1 over the square root of 15 sine radical 15 over 4t. Make sense? Okay. Now, with this expression and returning all the way up here to remind ourselves what this part here looked like, we just write down our answer. We know what the inverse Laplace transform of this type expression is. It's just a heaviside function times a shift. So, lowercase y of t, which is the solution to our differential equation, has the form u5 of t f of t minus 5 minus u sub 20 of t f of t minus 20. Okay. If you have what this looks like stated clearly, this is an acceptable form for the answer. Okay. Now, if you were going to write this out in full detail, what you would do is need to replace t everywhere it appears with t minus 5. And then in the second expression, everywhere with t minus 20. Okay. Now, I'm not going to ask you to do that on quizzes and exams and stuff. All right. It's just asinine. All right. This is fine. If you have a clearly defined expression for what f of t looks like and you write it in terms of shifts, that is sufficient. Unless I give you directions indicating that you have to write your answer in some different form. Oh, yeah, sorry, you're right. I forgot the over 4 here. All make sense? Okay, so previously, when I mentioned that this was going to be a test of our algebra skills, this is what I meant. Okay, there is a lot of tinkering to do in order to get the equation into the form that we need in order to match what's going on in the Laplace transform table. Okay, we need to be able to look at the table, see what the forms are. You're going to be doing a lot of factoring, a lot of completing the square, and a lot of partial fraction decompositions. Partial fractions decompositions involve solving systems of linear equations. All right, so doing this using calculus stuff, just worse. All right, so this is an easier path. Okay, but I recognize that there's a level of tedious calculation here that maybe people just don't do very much of because it's not very much fun. All right, but it is a necessary set of abilities. Okay, and the good thing about going through and doing this type of practice is it's a very good way to sharpen your other skills. All right, um, it's pretty common to make silly mistakes doing the algebra part of solving calculus problems. Okay, people will make mistakes simplifying expressions or writing things down like the product rule or whatever, or just making copy mistakes or whatever. This is a good way to combat that. All right, getting good at this. All right. One of the things that these is just inherent in the way that these problems work is that I cannot tell you what's going to happen problem to problem. All right. Everyone is sort of unique in terms of what algebra is necessary in order to work it out. All right. The remedy for not encountering things that you're not used to seeing is practice. All right. Drill yourself on these problems, do several of them. All right. You will eventually get a feeling for kind of how things are supposed to go. All right. There's going to be completing the square, there's going to be partial fraction decompositions. There are obviously going to be problems that are easier to do than others, but you're not always going to be given the easy problems. Okay. So let's do this example in Desmos so that we can see what this looks like, and then we'll go from there. All right, so what we have is, we'll call this thing f of t, and so we're going to have 1/2, and then e to the negative t over 4, and this whole thing's going to be multiplied times cosine of the square root of 15 over 4, and then we got a t here. We're going to add to this 1 over the square root of 15, and then that gets multiplied by sine of the square root of 15 over 4 times t. This should be the whole thing. Okay. Now, our y of t that we're making, get rid of that h, should have a 5 here and a 5 here. And then we copy this, subtract from it, except now we replace this with 20. All right, and then we want to zoom way in. Actually, let's set this stuff manually. Okay. And so here we're zoomed out far enough that we can see what the different behaviors are for this this expression. All right, see that it turns on at 5, it has a behavior, and then we turn off our forcing function, and that changes the behavior of the expression. Okay. This type of behavior is not something we'd be able to model without the ability to describe discontinuous functions on the right-hand side. Okay. So most of the problems that we work on for this class will have answers that end up looking something like the example that we just completed here. Okay. When we come back next class, we will add another wrinkle, another type of discontinuous function that has important application purposes for us. Okay. And what we'll talk about the different sorts of situations that models as opposed to just the unit step function or the Heaviside function, which in some ways acts as an on-off switch. Okay. The other function that we will talk about, which is called the impulse function, has a different purpose. We'll get into that next class. And we will find out that the impulse function solutions, when we need to work back to transferring from the frequency domain to the time domain, will give us things that look kind of like these shifted answers that we get from the Heaviside function. There's a relationship between these two things that we'll discuss a little bit as well. All right, so go practice. Okay, there's algebra to be done here. All right, and the way that you set yourself up to not get lost in the weeds on your quizzes and your exams is to have done plenty of practice problems. So please start working on that, and I will see you all next time.